Today, this is for class 10, that is science, magnetic effect of electric current. So, here, magnetic effect of electric current. It was found that when a current carrying conductor, if you place a compass needle near a current carrying conductor, the magnetic needle gets deflected. When a current carrying a compass needle is placed near a current carrying conductor, the compass needle gets deflected. We know that the compass needle is nothing but a bar magnet showing north and south direction. So this magnet is deflected. That means in the nearby region there must be some magnetic field. Only in the presence of a magnetic field in the nearby region of the compass, then only it is possible that the magnetic field will deflect. Again, it was found that when the current was switched off, then magnetic needle it moved to its original position. So, what does this prove? This proves that a current carrying conductor produces a magnetic field surrounding it. Now, in your textbook, before uh, mo- moving to the magnetic effect of electric current, it has been in this book about magnetic field. It is better that we must know about the magnetic field. What is a magnetic field? So, you know that if a iron piece is brought near a magnet, it gets attracted. So that means there is a force, and this force attracts the iron piece. So that is called the magnetic force. And this magnetic force surrounding a magnet forms a magnetic field. To demonstrate it, they have shown an experiment. You take a bar magnet, place it on a cardboard, and sprinkle some iron filling surrounding it. You tap the cardboard gently, you will find that the iron fillings will arranged in such a way that it will emerge from the north pole and it will end at the south pole. So from here magnetic field lines were drawn. That is, the magnetic field lines, it starts from the north pole and enters the south pole, and inside the magnet from the south pole it moves to the north pole. So it forms a closed loop. Here your magnetic field forms a closed loop. And it has been found that the magnetic field is more dense near the pole than in comparison to the equatorial region. So more dense the magnetic field lines, that is, its strength is more than compared to the equatorial region. Density of the magnetic lines is more near the poles, which means that the gap between the two magnetic lines are very small in comparison to the gap between the two magnetic lines in the equatorial region. And next important point is that any two magnetic lines never intersect at a point. If it intersects at a point, then if you place a compass needle there, at the same time it must show two directions, which is impossible. So the magnetic field lines never intersect. Now here comes that when a current carrying conductor, we find that when a current flows through a conductor, then a magnetic field is produced surrounding it. An experiment has been demonstrated in your book. You take a piece of cardboard and a conductor is passed through the cardboard. The cardboard is perpendicular to the plane of the cardboard is perpendicular to the conductor. Now you connect this conductor to a battery. When at the same time you sprinkle some iron fillings on the cardboard surrounding the conductor. When current flows through the conductor, you just slightly tap the cardboard. You will find that the iron fillings arranged in concentric circles. So magnetic field lines that are in concentric circles. So what will be the direction of the magnetic field lines? To determine the direction of the magnetic field lines, right hand thumb rule has been used. You hold the conductor with your thumb, with your right hand, and the direction of the thumb will give the direction of the current. That means you first of all you hold the uh, conductor and you place your thumb in the direction of the current. Your fingers, the direction of the curled fingers will show the direction of the magnetic field. So this is how we determine the magnetic field, direction of the magnetic field when a current is flowing through a conductor. Now again, it has been explained in a circular loop. In the circular loop, we find that as the current is flowing through the loop, on the one side, if the magnetic field lines are in clockwise direction, on the other side it will be in anti-clockwise direction. And if your loop is of greater radius, so at the center your magnetic field lines will be almost a straight line. Now comes your solenoid. It is an important topic because solenoid is practically used. Solenoid, it is nothing but it is a coil. A coil. And the most important fact here is that if a current flows through the solenoid, it behaves like a bar magnet. That means it magnetic field lines is it resembles the magnetic field lines of the bar magnet. And by the help of this solenoid, you can make magnets. That is, if you place a soft iron inside the coil, two things happens. Your strength of the magnetic field lines increases. At the same time, your soft iron gets magnetized. So this is used as an electromagnet and this is commercially used. So it is very important. It is a simple phenomenon. When a conduct coil, it is a simple coil made of conductor, and if current flows through the coil, it becomes a bar magnet and its magnetic field lines resembles that of the bar magnet. Now, our next topic is that is when a current carrying conductor, when a current carrying conductor is placed in a magnetic field, the magnetic field exerts a force on the conductor. Now, what will be the direction of the conductor? This is the most important factor because when a current carrying conductor is placed in a magnetic field, we know the direction of the current, we know the direction of the magnetic field. So, what will be the direction of the motion of the conductor? That so to determine the direction of the motion of the conductor, we Fleming's left hand rule has been used. In Fleming's left hand rule, the forefinger it is the magnetic field and the current it is the middle finger and the direction of the motion of the conductor is given by the thumb. Your four fingers gives the direction of the magnetic field and the middle finger it gives the direction of the current and the thumb it gives the direction of motion of the conductor. And these three fingers must be placed mutually perpendicular to each other. So here, by the help of Fleming's rule, and since a current carrying conductor placed in a magnetic field, the magnetic field exerts a force. Using this theory, the electric motor works. So here, if you place a magnetic field, that means two permanent magnets are placed and a coil is placed in between it. When the current flows through the coil, we find that according to Fleming's left hand rule, one side of the coil, the force is exerted downward, and the other side of the coil, the force is exerted upward, and it gives a half rotation. Now, next time, the side on which the force was exerted in upward direction, when it moves to the other side, that side the force is exerted downward, and the side where the force was exerted downward, when it moves to the other side, here the force was exerted upward. So we find that in every half rotation, the force are acted in opposite directions. Suppose on one side of the coil, if it acts downward, after half rotation, the that side the force is acted upward. So every half rotation we find that the direction of the force changes. So in this way it moves in an anti-clockwise direction and in this way it completes a cycle and this is how a motor runs. Now for commercial purpose, instead of permanent magnet, we use electromagnet, and the coil, with the shaft, there are number of turns in a coil. This is called as the armature. So this is how an electric motor works. Now comes our electromagnetic induction. Here, electromagnetic induction, when a coil, we take a coil and when a bar magnet, is moving inside and outside the coil, the bar magnet must not touch the coil. It will just move inside and outside the coil. What happens in the coil? there is change in magnetic field, and due to the change in magnetic field, an induced current is produced in the coil, and this phenomenon is called as electromagnetic induction. This is called as induction. So here, when the bar magnet, till the bar magnet moves in and out of the coil, we will get current in the coil, which can be detected by a galvanometer. When the bar magnet stops, there is no current in the coil. So what do we conclude? That whenever there is a change in magnetic field in the coil, we get an induced current in the coil. So here again, we know the uh, motion of the magnet. We know the motion of the magnet. And second, we know that is the um, uh, direction of the magnetic field. We know the direction of the magnetic field. We know the motion of the magnet, but we do not know the direction of the current. So, to determine the direction of the current, Fleming's right hand rule is used. Here again, the forefinger will show the field, the middle finger will show the current, and the thumb will show the motion of the your conductor. So now this principle is used in a generator, electric generator. So here, if you are moving, that means between two permanent magnet, a coil is placed, and when you rotate the coil in the magnetic field, there is change in the magnetic field inside the coil, and due to which current is produced in the coil. Now the direction of this current can be determined by the help of Fleming's right hand rule. That means if you place your Fleming's right hand rule at one edge of the conductor, you will find that your forefinger will give the direction of the magnetic field, and your thumb will give the direction of the motion of the conductor. That means we are rotating in anti-clockwise direction. Then the direction of the current will be determined. Again, on the other edge of the coil, again we will apply the Fleming's left hand rule. So here we find that in the earlier age, if the current was flowing in forward direction, in the other age, the current was flowing in downward direction. Now, after a half rotation, the current, the side in which the current was flowing in forward direction, when after half rotation, the current will flow in downward direction. And the current on the side which was flowing on the downward direction, after half rotation, the current will be flowing in the upward direction. So we find that after every half rotation, the direction of the current changes. So we find that every after every half rotation, the direction of the current changes. So it produces an AC current, that is an alternating current. Now, in this alternating current, we use slip ring. Now, if you have to, if you want a DC current, that is a direct current, it is a unidirectional current. If you want a DC current, then instead of slip ring, there must be split ring. So because of this splitting, one side of the splitting, the direction will be always in the upward direction, and the other side of the splitting, it will always in the direction, in the downward direction. So one side of the splitting will always be positive, and the other side of the splitting will be always negative. So in this way, we are going to get a direct current. So AC current, it is an alternating current where your current changes after every interval of time. But in direct current, we get a unidirectional current. So in our country, the frequency of an AC current is 50 hertz. One, there is a great advantage of AC over DC. For long transmission line, AC current is recommended. For long transmission of electric current, AC current is recommended. Now we come to our domestic appliances. Here in our house, there are two type of circuit. One is 5 ampere circuit and another is 15 ampere circuit. The 5 ampere circuit is used for bulb, that is 60-watt, 100-watt bulbs, or for fans we use the 5 ampere current. But if you have to, if there is a geyser or a room heater or an AC, then we require 15 ampere current. Now you have seen the cables. Inside the cable there are three colors. One is the red, other is the black and the green. The red color represents the live wire, which is considered as positive, and the black color is considered as neutral, which is considered as negative, and the green color is considered as earthing. So in electric circuit, earthing plays an important role. How? Any electrical instruments made up of metal body, earthing is necessary. Why? Suppose if your live wire, the insulation of the live wire gets damaged and your live wire comes in contact with the metal body, then your whole metal body current will be flowing through it. And if anyone touch it, he will get a severe shock. But if there is a provision of earthing, then most of the current will pass through the earthing, and the you will get a shock, but it is a very light shock, and it will prevent you uh, from further damage. So any ma- electrical instrument whose body is made up of metal, earthing is very necessary. Now about fuse. Here fuse, it uses the Joule's heating effect. A fuse uses the Joule's heating effect. So in an electric circuit, fuse is used. Due to overloading or because of some abrupt flow of the current, to protect your electric circuit or to protect your costly electrical instrument, fuse is necessary. When there is an abrupt flow of current due to Joule's heating effect, the fuse wire melts and it gets disconnected. So the flow of the current stops and your electrical gadgets remains safe. And because of overloading, short circuit can also happen. Usually short circuiting, when the insulation of live wire and neutral wire gets damaged, and if these two wires come in contact, short circuit takes place. There is and for a few seconds there is an abrupt flow of the current, and because of overloading also short circuit may take place. So fuse plays an important role in electric circuit. So this is all about your magnetic effect of electric current. Thank you.